In this video, we're going to talk about 9.4, which is the comparison of series. And we're going to use the direct comparison test to test for convergence or divergence of series. And we're going to use the limit comparison test to test for convergence or divergence of series. So far, the terms in a series have been fairly simple. But if we have a slight variation from those special series that we have studied so far, it can make our tests inapplicable. So for example, we start off with a geometric series here, 1 over 2 to the n. But if we change that numerator to be n, so it's n over 2 to the n, we can't use the geometric series test anymore. The next one, we have a p-series of 1 over n cubed. And so if I make that 1 over n cubed plus 1, it's not a p-series anymore, and I can't use the p-series test. The last one is one that I would use the integral test for. N over n squared plus 3 quantity squared, because I see a u du substitution there. But if I would make that numerator n squared over n squared plus 3 squared, no longer have that nice u du substitution. So this one is no longer geometric. This one is no longer p-series. And this one is no longer easily integrable. Okay, so what we're going to do though is in this section, we're going to try most of the time to choose something that is geometric or p-series that we know the convergence or divergence of, because we know that with those series pretty easily, and use that for comparison. So those are the two types of series that we're going to try to use for comparison when we can. So we'll learn two new methods for studying positive term series. First, we'll use the direct comparison test here. So the direct comparison test for positive term series tells us that if an is greater than 0, because it's positive, is always less than or equal to bn for all n that are elements of the natural numbers, or that at least are elements in the series that we're discussing. Then if n equals 1 to infinity, the series of bn, if that converges, if bn converges, then the series for an from n equals 1 to infinity also converges. I'll draw a picture of that in a little bit in the notes, and it'll make more sense there. But if the bigger one is an upper bound for the lower one, and the bigger one converges, the smaller one also has to converge. So if the smaller one limit or summation from n equals 1 to infinity of an, if it diverges, it's going to shoot off to positive infinity because it's a positive series. So if it's going to go up to positive infinity and it bounds bn below, then bn is also going to have to diverge to positive infinity. So let's look at an example here to determine the convergence or divergence of the series n equals 1 to infinity of 1 over n to the 3 halves plus 6. This looks a lot like n equals 1 to infinity of 1 over n to the 3 halves, which is a convergent p-series. So because our comparison series converges, then we are going to make sure that it is the one that is greater than AN. So let's check that. Let's make sure that 1 over n to the 3 halves is greater than or equal to 1 over n to the 3 halves plus 6. Does that make sense? Let's cross multiply. N to the 3 halves plus 6 is greater than or equal to n to the 3 halves here. Yes, when I subtract n to the 3 halves from both sides, 6 is greater than or equal to 0 for all n greater than or equal to 1. Check. So that's correct. So let AN be equal to 1 over n to the 3 halves plus 6, and Bn be equal to 1 over n to the 3 halves, since 0 less than An, so they're equal to Bn for all n. It's an element greater than or equal to 1, and Bn converges by the P series test. An also converges by the direct comparison test. From this point forward, I'm just going to say DCT for that, for direct comparison test. All right, let's draw a picture of this and say that we have 0 less than An is going to be in blue, less than or equal to Bn is going to be in green, and this is going to be convergent. Then we have something that looks like this, going maybe closer and closer to 0 down here. Then this is going to stay below that, not necessarily by a fixed amount, but maybe getting smaller even quicker. We don't know, but it's eventually going to have to go towards that same, it's going to get pushed down towards 0 like that if it's staying below that series that bounds it above. Make sure this one comes down. So these are all monotonically decreasing here, like that. All right, so key idea here is Bn is bounding An from above, and An is positive. So if Bn converges, An also converges like that. All right, let's move on to the next one. And this is going to be one that's going to diverge. We're not going to get the answer right away. We're going to think that we should do something, and I'm going to try what looks most obvious here. and it's not going to work, and then we're going to have to figure out how to fix it. So I'm just going to tell you that the first stuff that I write down here is thought process and working through it and trying something, and it's going to be wrong. So just heads up. So let's look at this series 1 to infinity of 1 over n to the 1/2 plus 3. And it looks like the series n equals 1 to infinity, 1 over n to the 1/2, which is a p series that diverges, right? And so if we try and let an be equal to n equals 1 to infinity of 1 over n to the 1/2, and we let bn equal n equals 1 to infinity, 1 over n to the 1/2 plus 3, then we need to show that an is less than or equal to bn. Show for all n greater than or equal to 1. Let's see if that's true. So 1 over n to the 1/2, we need that to be less than or equal to 1 over n to the 1/2 plus 3. I already know this is not going to work because this is the bigger denominator. It's the smaller fraction. So cross multiply here, n to the 1/2 plus 3 would need to be less than or equal to n to the 1/2. And this is false. It's never true. So try to find a different divergent series that will bound bn below. Okay, so here's what we want and what we got so that you can have an idea of what's going on here. So right now we have an is going to be in blue, and we have 0 less than that, less than or equal to bn is going to be in green again. And this is the one chosen for comparison. And so we have a situation where bn is going like this. Let me say this is the one that's given. And we have bn is maybe going something like this and then rising kind of quickly here, like so. Okay, that it's kind of going like this. Now we want to find an an that maybe isn't always below the green line, but maybe we can find it where like this trying to keep these dots lined up here. So it's also going to go off to infinity here, but maybe it crosses somewhere here between, say, 3 and 5. So maybe by n greater than or equal to 4, it satisfies the condition that bn is going to be greater than or equal to an. We don't necessarily have to have this true starting at term number 1. What we can't have is we can't have a situation where, and I'm going to draw this in pink here, we can't have a situation where I have a series like this that is going to be divergent but stays below bn all the time. That's not allowed. I also can't have one, I call this one kn. Kn does not help us because it does not bound an above. I think I drew these backwards. Let me look. Need to be bounded below by, this is, if I choose a series that doesn't meet the conditions where it's always in the wrong place, then it's not going to help me. That's what I was trying to draw there. But I'm just going to let the example here help me out. So pick another series that is easy for us. It's a P series, geometric series, something like that. I'm not going to worry about Kn here. Don't worry about that part of my picture. So the important thing is for you to see that I can pick something where they're going to cross each other and these conditions are still going to be met here, that at some point an is going to be less than or equal to bn for all n greater than or equal to some value there, like 4 in my picture. So we must bound a divergent series below by another divergent series in order to conclude divergence by the direct comparison test. Back to our series. So what P series that diverges bounds 1 over n to the 1/2 plus 3 from below? Let's try, and we want this to be the one that's below. So try an equals 1 over n, and bn equals 1 over n to the 1/2 plus 3. So I want 0 less than an less than or equal to bn for all n, well, greater than or equal to something. I'll figure out which n that's going to be for. So let's try 1 over n less than or equal to 1 over n to the 1/2 plus 3. And this is going to be n to the 1/2 plus 3 is less than or equal to n. So I'm going to bring this over here and say 0 is less than or equal to n minus n to the 1/2 plus 3. Let u be equal to n to the 1/2 here. less than or equal to u squared minus u plus 3. And then I'm going to solve that there and say, and I can use a graphing calculator here as well. Let's see if I can factor this here. No factors of 3 that add up to be -1. So let's try this. Yeah, let's go ahead and let's look at these two functions here, and let's see where they cross each other on a graph. That's going to probably be the easiest way for me to make my choice. So I have f1 of x is equal to x. f2 of x is the square root of x plus 3. Now I want to find that point of intersection. So let me go ahead and use Desmos here to do that for you. Graphing calculator, y equals x, and y equals the square root of x, and then plus 3 on the outside. And that point of intersection there is after the number 5. So I need to choose n greater than or equal to 6 for this to work, since this is 5 point something something something. So any number bigger than 5 will be fine. Just pick something sufficiently large that's bigger than 5. So the first perfect square that I know about off the top of my head that's bigger than 5 is 9. So let's use n equals 9. So a value of n equals 9 will work nicely. So let's just show that 9 to the 1/2 plus 3 is less than or equal to 9. 3 plus 3 less than or equal to 9. 6 less than or equal to 9. And that relationship is going to stay true forever, and on and on and on. So at least from at least n equals 9, 10, 11, so on and so forth, 0 less than an less than or equal to bn, like that. Thus, since from n greater than or equal to 9 at least, thus, since for n greater than or equal to 9, 0 is less than n equals 1 to infinity of 1 over n, less than or equal to n equals 1 to infinity of 1 over n to the 1/2 plus 3. And n equals 1 to infinity of 1 over n diverges by p series equals 1 to infinity of 1 over n to the 1/2 plus 3, also diverges by direct comparison test. All right, so summary of the direct comparison test here. If you're using the direct comparison test to conclude that a series converges, find a series that's bigger than it that converges, that bounds it from above. If you're using the direct comparison test to conclude that a series diverges, find a series that's smaller than it that diverges to bound it below. All series discussed here must be positive. 0 is bounding the series from below. Now, I'm going to show you how I would do this problem that I think is easier. And yeah, so let me show you what I would do to choose my series for this example that we just did. I just followed what the textbook would do here, but I'm going to take n equals 1 to infinity, 1 over n to the 1/2 plus 3. I know that it's related to n equals 1 to infinity of 1 over n to the 1/2. But I know that that's not going to work. That's bigger. So I want to multiply the denominator by something to force it to always be smaller. So how am I going to do that? I'm going to say that I'm going to make this, I want the smaller one. So an, I'm going to choose to be n equals 1 to infinity, 1 over n to the 1/2 plus, and I'm going to bring this power up to match this power like that to make this n equals 1 to infinity of 1 over 4n to the 1/2. Check it out on your calculator if you want to. I'm actually going to do that right now for you. 1 over x to the 1/2 plus 3 and 1 over 4 x to the 1/2 power. So let's go ahead here and zoom in, and for all, they cross each other right there at 1, and for all n greater than or equal to 1, then my chosen series that I know is divergent because it's a p-series that diverges is less than or equal to my given series, and I'm in great shape. So they may cross each other at n equals 1. That's okay. So for all n greater than or equal to 1, I've chosen an an that is positive and less than or equal to bn. I've forced that to be true, and I know an diverges by the p-series test. P equals to 1/2. Therefore, bn, which is also diverges by direct comparison test. To me, that's how easy that should be to use the direct comparison test, that we're either going to remove terms like we did the first time or bring terms up to match the power. So that would be what I would do in that case. Let's go back to our summary here. If you're using the direct comparison test, yeah, again, make sure that if you want it to converge, that it's big, that you choose a bigger series that also converges, that bounds it from above. If you're using the direct comparison test to conclude that a series diverges, find a series that's smaller. then it that diverges and bounds it below. All series discussed must be positive, zero bounding the series from below. Perfect. All right, so let's go ahead here and start talking about the limit comparison test, which many times is actually easier to use than the direct comparison test. When you get told to just use a comparison test and don't get told that you have to use the direct comparison test, many times you're going to choose the limit comparison test because of how much easier it makes your life to not have to particularly pick one that's above or below. You just need to pick one that you know its behavior. So you're going to choose a p-series or a geometric series. So choose a p-series or geometric series most of the time. Usually. All right. So if AN is a positive series, BN is a positive series, and the limit as n goes to infinity of AN over BN exists and equals L, where L is finite and positive, then AN and BN both converge or both diverge. I'm going to force it to be finite and positive. I'm actually most of the time going to force it to be 1. It's easy to force it to be a positive 1 to make this test work most of the time. So use the limit comparison test to determine whether the series 1 over n cubed minus 1/2 converges or diverges, where your let's look at the nth term test here first. Limit as n goes to infinity of 1 over n cubed minus 1/2 is going to go to 0, so no info here, but we start there, right? So let's compare to something that it looks like. Let's let Bn be equal to 1 over n cubed. That's a p-series that I know what it does. It converges. So I want to find the limit as n goes to infinity of an over bn equals the limit as n goes to infinity of n cubed over n cubed minus 1/2 is going to be times 1 over n cubed times 1 over n cubed is limit as n goes to infinity 1 over 1 minus 1 over 2n cubed. It's 1 over 1 minus 0. 1 over 1 is 1. So since that limit, since limit n goes to infinity of an over bn equals 1, which is greater than 0, is finite and positive, then n and bn both converge or both diverge. Bn converges by the p-series test. So AN also converges by the limit comparison test. From this point forward, I'm going to write L period, C period, T period to stand for limit comparison test. All right. Now let's use the limit comparison test to determine whether the series of the summation from n equals 1 to infinity of the square root of n over n squared plus 1 converges or diverges. So I'm going to choose the most powerful thing in the top and bottom to be my Bn. That's going to be n to the 1/2 over n squared. It's going to be n equals 1 to infinity. Bn is going to be uh, 1 over n to the 3/2. So AN is going to be this right here. And so I want the limit as n goes to infinity of AN over BN is going to be root n over n squared plus 1 over 1 over n to the 3/2 is equal to the limit as n goes to infinity of, that's going to turn into n squared over n squared plus 1 is definitely equal to 1 because degree of the top and bottom are the same. Ratio of the leading coefficients is 1, which is positive and finite. So summation of AN and summation of BN both converge or both diverge. Summation of BN converges by p-series test. P equals 3/2, which is greater than 1. Therefore, summation of AN also converges by the limit comparison test. There's a little bit more to write, I think, with the limit comparison test, but I think it's a much easier test, and I'm willing to write a little bit more there for it. So now let's go ahead and see what's going on here with this one. So determine the convergence or divergence of n 2 to the n over 4n cubed plus 1. So let's come up with a Bn that we are sure that we know what it's going to do. And we may know what it does because of p-series, geometric series, integral test, anything. So let's try a limit comparison test here. We'll try the ratio test on this one later. once we learn it. So just note that we'll see this one again in our notes later. So let's choose a BN here. We know AN is going to be N 2 to the N over 4N cubed plus 1. Let's choose a BN that's N 2 to the N over, that 4 is not important, over N cubed, like that. So this is going to be 2 to the N over N squared. So we're only choosing the powerful things to look at. So I need to keep track of this multiplication that's going on here and this exponential down here, but the coefficient here isn't important. The addition isn't important. They're trivial compared to how quickly these other things are growing here. So now exponentials grow faster than polynomials here do. So Bn is going to diverge by the nth term test. Right? Let's go ahead and prove that to ourselves that the limit as n goes to infinity of Bn is going to be limit as n goes to infinity of 2 to the n over n squared. We're going to use L'Hopital's rule. That's limit as n goes to infinity, ln of 2 times 2 to the n over 2n is equal to limit as n goes to infinity of ln of 2 squared times 2 to the n over 2 goes to infinity. So that said, then we're going to come back to the limit comparison test now and say, okay, we know that AN and BN, actually, let's find the limit of them. Sorry. Limit as n goes to infinity of AN over BN is equal to limit as n goes to infinity n 2 to the n over 4n cubed plus 1 divided by n 2 to the n over n cubed. So this is going to be equal to, write it this way, limit as n goes to infinity and 2 to the n 4n cubed plus 1 divided by n 2 to the n over n cubed equal to limit as n goes to infinity and 2 to the n 4n cubed plus 1 times n cubed over n 2 to the n. So this and this cancel each other out, and I'm left with limit as n goes to infinity of n cubed over 4n cubed plus 1. And this is going to be equal to 1/4. If I had chosen my Bn to have a 4 down here, a 4n cubed, then this would have definitely just gone to 1. But this is okay that it goes to 1/4, which is finite and positive. So AN and BN, the summations both converge or both diverge. Summation of Bn diverges by the nth term test. Therefore, summation then goes from 1 to infinity of An also diverges by the limit comparison test. Let me just look at one thing. So, summary of our limit comparison test right here. Find a series whose behavior you know or can easily show. And that will lead to fortunate cancellations when taking a ratio. Take a limit of the ratio with the intention of getting a finite positive limit. If at first you don't succeed, try again, right? If limit as n goes to infinity, an over bn is not finite and positive, use another test. All right. Probably the ratio test. We'll learn about those later. All right. Next time when we come back, we'll talk about the alternating series test. It is another one that has some conditions that have to be met, not nearly as many, but it's going to introduce a new topic of something we call absolute convergence. So it'll be important for you to understand that. So far, we've only talked about series that have positive terms. In the alternating series test, we're going to have terms that alternate between positive and negative, and we're going to have to figure out how to deal with those types of series without having to do the method that we used in the beginning with the limit of the partial sums. All right, I'll see you for the next video.